Hello, this is Jishan Chowdhury from JC Tuition, and today we're going to be discussing Kirchhoff's laws. So Kirchhoff's first law states that the sum of the currents entering any point in a circuit is equal to the sum of currents leaving at the same point. So basically we've got this, current is a measure of charge, and we've got this law of conservation of charge where the sum of the currents is equal to the sum of the currents leaving. So currents entering versus leaving. So very simply, we could, if I draw a diagram, and this is just the point P. Let's say this is the first current, call it I1, and this is the second current. Well, we know the current at the point P must equal current going into it and the current. So we can just say I1 is equal to I2. Pretty simple. But let's say we maybe added some branches. So again, we'll draw some branches. Let's say this is the point Q. So let's say instead this time current entering here, I1, and it branches out into I2 and I3. Well, again, we know the sum of the currents entering at any point is equal to the sum of the currents leaving at the same point. So again, using this sort of law of conservation of charge with Kirchhoff's first laws, we've got that. For this, we've got I1 is equal to I2 plus I3. So if we just imagine billions of electrons entering the same point in the circuit at a certain time interval, let's just say a second, we know that 1 billion electrons must exit these points exactly at 1 second. You can test this if we attached ammeters. So if we touch ammeters and we know we attached them in series so that we can measure the charge going through them, you can actually test this idea and you'll see Kirchhoff's first law in action. So is there a way we can sort of generalize this idea? Well, yeah, we can just say we can use this Greek symbol sigma, which means the sum of. The sum of all the currents in is equal to the sum of all the currents leaving another point. And that, in a nutshell, is Kirchhoff's first law. So given that there was a first law, Kirchhoff must have a second law, and the second law states that the sum of EMFs, that's electromotive forces, around any loop in a circuit is equal to the sum of the potential differences around the loop. So again, we've sort of got this law of conservation of energy, don't we? Just in case you've forgotten, EMF is the energy provided or gained per coulomb of charge. Potential difference is the energy lost per coulomb of charge. So yeah, we've got a law of conservation of energy. So let's consider a loop. What do you mean by a loop? Well, here's one loop. It's just a simple series circuit. And yeah, so we've got a cell and we've got two resistors here, R1 and R2. Well, and in terms of Kirchhoff's first law, well, because it's a simple series circuit, we know the current is the same the whole way around. So let's just forget about that for a moment and just focus on the second law. So the sum of the EMFs around the loop. So if in this case, the EMF is provided by the battery, so we've got E is equal to the sum of the potential differences. Well, the potential differences are the energy lost per coulomb is lost across the resistors, right? So we can say the EMF of the battery is equal to the potential differences of the resistance. Now, you might remember potential difference is current times resistance. That's Ohm's law. So in this case, we've got current times, well, the resistor 1 plus the current of resist and times the resistor 2. So again, if we were to try and give a generalization, we've got the sum of the EMFs is equal to the sum of the potential differences, and that is Kirchhoff's second law. So let's just add some numbers in to sort of try and make sense of all of this. So here we've got a series circuit, so the current is the same the whole way around. Let's see if we can work out this current using Kirchhoff's second law. So just a reminder, Kirchhoff's law is the sum of the EMFs is equal to the sum of the potential differences. So let's calculate the sum of the potential differences first. So we've got current times the resistance. So we don't know the current, it's just I. So we've got 10 times I at this first resistor. And we've also got this second resistor. And we've got 30 ohms resistance. And the current again is unknown. So that's just 30. So 10I plus 30I, we can collect it together to say 40I. Okay. And let's also try and work out the sum of the EMFs. So batteries are connected in opposite ways, as you can see. So that means one of them EMFs must be negative. So we can say it's 6 volts in the positive direction, and this one's connected the other way, so we know this one must be negative. So we can take away 2 volts, and that means the sum of EMFs is 4 volts. And now, using Kirchhoff's second law, we can equate these. So we can say 4 volts is equal to 40I, and we can just divide 4 by 40 to make I the subject of the formula. So 4 divided by 40 is of course 0.1 and amps, because we're measuring current. So that's Kirchhoff's second law, and I hope that makes sense. Okay, and to sum up this video, I want you guys to apply Kirchhoff's laws for this circuit here, and I want you to work out the currents flowing through the resistors. So I want you to work out I1 with this resistor and I3 for this resistor. Okay, so hopefully you've been able to have a go. So let's apply Kirchhoff's first law at this point here, P, where we know that the sum of the currents going in at any point is equal to the sum of the currents going out. So that means at the point P, I1 plus I2 is equal to I3. Cool. Let's enable this equation 1, because we might end up with a lot of equations here. Now we've got 2 loops, if you'd like. So to apply Kirchhoff's second law, I'd recommend splitting up the loop. So let's just focus on this first loop here. Yeah. So Kirchhoff's second law, so the sum of the EMFs states that the sum of the EMFs is equal to the sum of the potential differences around a loop. So look, considering this first loop, sum of the EMF is simply 6, and some of the potential differences. So we've got this first resistor again to work out the potential differences. We've got current times resistance, so that's 30 ohms of resistance times I3, so that's 30, and obviously there's this resistor here again. We've got I1 running through it, 10 ohms of resistance, so we've got 10 times I1. Not much else we can do with that, so let's just leave that and call that equation 2. We can apply Kirchhoff's second law again. Let's use this loop here. So again, we've got sum of the EMFs, in this case is 2, and that equals, there's just one resistor here again, it's just the same, 30 times I3. If there's only one unknown, we can actually divide both sides by 30 and we can figure out I3. So I3 in this case is 2 divided by 30, or 1 over 15. And let's call this equation 3. Because we know I3, actually, we can plug it back into equation 2. And that'll give us one unknown, and we can work out I1. So let's say equation 3 into equation 2. Well, we've got 6 equals 30 lots of I3, but we know I3 is 1 over 15, so we can just plug that in, replace it, plus 10 lots of I1. Well, the 30 and the 15 just cancel out, so we've got 2. We can do 6 take away 2, so now we've got 4 equals 10, and the first current, and then we can simply divide by 10 amps, so we get I1 equals 4 divided by 10, so that's 0.4 amps. So yeah, we've already got I3 and I1. But let's just work out I2 for the heck of it. But we can, now that we know I3 and I1, we can actually use equation 1. So if we just rearrange equation 1, we can say that I2 is equal to I3 take I1. So we know the value of I3 is 1 over 15, and the value of I1 is 0.4. Plug that into our calculator. That's minus a third, or minus 0.33 amps. 2 decimal places, that's I2. So it's negative. What does that mean? Well, it means that actually the current's flowing in the opposite way. So this arrow actually should be facing the other way. Yeah, so that's how you apply Kirchhoff's laws. I hope that makes sense to you now. And if you would like any more support, please visit our website, www.jctuition.net, where we have plenty of free resources in physics and other subjects. All right, thank you.